Hello everyone! Today we're going to be doing a problem in Newtonian gravity. So what we have here is we have two uniform identical spheres that are held in place in the locations drawn, so 16 centimeters separated along the same axis. They each have mass 0.260 kilograms, so they're identical spheres. And what the problem asks is to find the magnitude of the initial acceleration, so just right when you release a third sphere of mass 0.01 kilograms that's held above. So it's sort of 6 centimeters above here. If you do the math, you see that it's 10 centimeters directly from the center of the smaller sphere to A, similarly 10 centimeters to B. This is a very symmetric problem. And so again, what we have is we have these two spheres that are going to create a gravitational field, and then we have a third sphere here that is going to be pulled to them by the force of gravity, and we're asked to find the initial acceleration right at the instant when you release that sphere. So again, what is the initial acceleration of, we'll call it C, where again A and B, the spheres at locations A and B, are just held in place, so they aren't going to move. We just have C that's going to be pulled to them by the force of gravity. So what we're doing here is just Newtonian gravity, and so the main equation that we need is the force of gravity is equal to big G, and then mm of whatever two masses you're considering the force between, divided by r squared, where r is the distance between the two objects, and then in the r hat direction. And what I mean by the r hat direction is that if we start at C and draw a vector to A, the force of gravity between these two objects, this would be r, is along the direction of the vector connecting the two objects. So one of the key things that we are going to use in this problem is the fact that generally when you think about this equation, you might be thinking about just point particles of mass little m and big M. We know if we have extended objects with some funny shape, then you would have to consider the force of each little element. But here what we have are spherical objects, and the nice thing about those is that spherical objects can always be treated as though all of their mass is right at the center. So we can treat these as both point particles and then just blindly apply this equation, and everything will work out well. All right, so let's look at our little guy C. And what we see are there are two forces acting on it. There's what I'll call F A and FB. So the force of gravity due to A and the force of gravity due to B. And then we can break this up into components, and we have FA, we'll call this the x direction, and FB in the x direction. That's too small a little bit, sorry, FAY, and then FBY are both pointing down. So again, I just took the force vectors, FA and FB, and broke them into their components along the x and the y direction. And part of why I did that is what we'll find is because this system is symmetric and A and B are exactly the same, what we'll find is that FAX as a vector is equal to negative FBX. So they're pointing in opposite directions. These masses are exactly the same distance away, at the same angle, with the same mass. And so this is going to tell us automatically that the sum over all of the forces in the x direction is 0, because those two pieces are just going to cancel out. And what we'll find is that the mass is just going to be pulled directly down. It'll have equal pull from either side, and so the net acceleration is just simply going to be in the y direction, so in the downward direction. All right, so now what we need is to find then the magnitude of these forces in the y direction. So what we can do is draw a little triangle here. So we have, sorry, I'm not drawing things to scale at all. We could draw some angle theta, which is this theta here. And if this is 6.0 centimeters, and this is 8.0 centimeters, this is 10.0 centimeters, what we find is that sine of theta is opposite over hypotenuse, so 8.0 centimeters over 10.0 centimeters. And cosine of theta is 6.0 centimeters over 10.0 centimeters. And let's switch to a different color. And so we can compute the force due to A in the y direction. So again, that's going to be the force along this direction. The downward force is going to be given by FA, or just FA, so the total force, magnitude of the force, times cosine of theta. Because again, this is the y direction, so we want the adjacent side. So that tells us that it's cosine of theta, which we just learned here what cosine of theta is, so we'll be able to plug that in. But again, what is f of a? Here we just apply the force of gravity, Newton's force of gravity, and we see that this is g, so we'll call this little m, and then both of these are the same value, big M. So g, just as I had written, gmm over, I'll call this 10 centimeters r, as I had before, r squared times cosine of theta. Again, this is just, I'm just writing the magnitude here. And then again, because of the symmetry of the problem, what we see is that this is equal to fby, which is to say that the force due to the B, now it's along the same direction, but it's the same magnitude as the force due to A. All right, so what we find is that the total force in the y direction, Fy, is equal to the sum of these terms, 2gmm over r squared cosine theta. And what we're asked for is actually the acceleration, not the force. And so I can write using F equals ma. A in the x direction is F over m. And then divide by m, and these are going to cancel. And so the acceleration is simply 2g big M over r squared cosine theta, or again, cosine theta is 6/10. So if we plug in all of the values, look up the value of g, we get that this is 2.1 times 10 to the negative 9 meters per second squared. So a pretty small little acceleration, but there you have it. And again, if we want to make this a, oh, that's a y, not an x, in case that's not clear, y. If we want to make this a vector, of course, we know it's all in the y direction, so I'd call an arrow and y hat, and if it's in the negative direction, it would be negative. But there you have it. So again, we're left with only acceleration in the y direction because the forces in the horizontal direction between A and B canceled out because of the symmetry of the system. All right, thanks for watching.